Welcome to Chemistry 111. Okay, continue with Chapter 8, where we talk about chemical reactions and aqueous chemistry. Quick reminder, since this is the week of fall break, we will not be having lab this week. We may not even have much of a class on Wednesday. So if you are, not here, I don't think I'll be holding that against you. Now, if you want to show up, get some help with something or another, that's fine. Worst case scenario, if I feel like I need to go over anything, I'll put out a video. You can watch that in your free time. But I probably won't be live streaming something. I'll just see what's all going on. But I will send an email about that when I'm 100% sure. In the meantime, let's look at this. So, common types of reactions. We did go over this very briefly last class, but just a quick reminder. So, most reactions can be fitting into these five basic types. And they can further be classified by other ways. But the basics are combination, two things become one. Decomposition, one thing becomes two. Single displacement, an element and a compound switch places. So an element goes into a compound produces a pure element. Double displacement, where two cations switch places between compounds, and combustion, which is kind of like a single displacement where oxygen comes in and makes some oxides out of a bunch of stuff it burns. And we finished off last class by talking about driving forces, that essentially we need something to push these forward. We need some reason for them to happen. Because what we'll learn in second semester is there's actually a natural state of equilibrium. I know we draw an arrow pointing to the right as we work through this, but there's often an arrow that can point right back. The same way as you can roll a ball down a hill, it is possible to push that ball right back up the hill. And what you want in a reaction is, say, a hill of sufficient steepness that ball is not going to be able to roll right back. We're going to need energy to put it back. We need something. We need like a steep hill, some way to remove a reactant or a product so that it won't go back. So as I said, sometimes we form a solid. Sometimes we take two aqueous chemicals and form a liquid. Sometimes we're going to transfer electrons and to get to a lower state. And we're going to look at these types of reactions each in turn. In fact, we'll do a lab about, I think, acid-base chemistry and oxidation reduction chemistry in the following weeks after fall break. So first thing we need to think about is how solutes dissolve in order to talk about what does it mean to be aqueous chemistry. I mean, it's pretty easy to think about a solid. A solid is a series of compounds just bonded together in a never-ending chain, or close to never-ending chain, in millions and millions of tiny little molecules stuck together. You can think of a liquid as tiny little covalently bonded compounds kind of swishing over each other, but they're all essentially the same. A gas, you just move them so far away they stop interacting. Well, what's a solution? What does it mean to be a solution, especially an aqueous solution? So when a solid dissolves, it's said to be soluble, and if any of it remains undissolved, it's said to be insoluble. But this dissolution occurs because of what's called a solvation. Essentially, what happens is the water surrounds each individual atom or each individual compound and essentially swallows them up. The reason we no longer see the solid when it dissolves is because we've moved each individual ion or particle to a sufficient distance away from the other particles that we no longer notice them. If you take some salt crystals, you can see the salt crystals even if they're really tiny. But if you were to cut it up smaller and smaller and smaller, eventually you'd get to a point where you couldn't see the salt crystals you're cutting. That's the same concept when we're dissolving something. Water is cutting the salt crystals up to smaller and smaller and smaller till we get to individual atoms. And each individual atom is surrounded by dozens, if not hundreds, of water molecules. And what we're seeing is just the water, and the salt's still there, but it's just so far separated that it's no longer visible to the naked eye. So this happens because water is polar. We talked about this last chapter. Polarity, because we have that dipole of the oxygen being partially negative, the hydrogens being partially positive, and most things that will dissolve will also be polar. So most salts are ionic. Remember, what is ionic? It has a full cation and a full anion. And the cation will be attracted to the oxygen's negative. The anion will be attracted to the hydrogen's positive. And so the water molecules will rearrange themselves in order to have the maximum attraction between the cation in water and the anion in water. So I've kind of drawn an image of what that is. Instead of Na stuck with Cl and right next to each other, we have 4 or 5 different weaker attractions, but 4 or 5 weaker attractions are still better than one strong attraction. So they're surrounding them and pulling them away from each other. And all this empty space between is just going to be filled with water molecules. Water molecules that are essentially separating these guys like a crowd at a dance. Sodium can't see the chloride. There's too many molecules between them. Now, we can break soluble compounds into 3 types. Soluble means it will be surrounded by water and dissolved, but these guys don't always have the same properties. When a compound dissolves fully into ions, meaning it will split apart as good as it will get, be essentially 100% separation. We would call this a strong electrolyte. We call it electrolyte because if you run a current through a strong electrolyte, it will produce a strong current. You get full electricity. I'd love to do a demo right now, but it's a little tricky and I have to have it set up. Maybe I'll try to do it in lab next week. But I have to borrow something from Dr. Johnson. I have to borrow a circuit and like a light bulb. But if you run electricity through this, strong electrolytes conduct strongly. Now, some compounds, they will dissolve, but they will not break into ions. They are also polar, but non-ionic. A good example would be sugar. Sugar will stay as a sugar molecule, but it won't break apart. Ethanol will dissolve in water, but it will remain a whole ethanol molecule. It will not break apart because these guys are all built up of covalent bonds, not ionic bonds. And so when they dissolve, they will produce no ions, and thus they will not conduct electricity. They will be non-electrolytes. And like most things, there's a possibility to have somewhere in between. You can either have all separation or no separation, but you could also have the partial separation. Basically, what happens is when you dissolve these compounds into water, they will separate fractionally. What does that mean? It means there'll be some portion that separate and some portion that do not. Example of this would be vinegar. This is a weak acid. A weak acid, meaning that instead of going 100% to ions, it's going to go maybe 10% to ions. The rest of it stays together. And so when they conduct electricity, you get a very poor current. When I do this demo in a week or so, if I remember, please try to call me on this so I'll try to remember, is you can light up a light bulb by mixing salt and water and then running a current through it. If you use a non-electrolyte, light bulb stays dark. If you use a weak electrolyte, the light bulb lights up very dimly because it doesn't get enough energy to fully produce the light. If I put, say, sodium chloride in there, we get a strong current and the light bulb lights up bright as if normal. So these weak electrolytes are weak because if I have a covalent compound like acetic acid, CH3COOH, this is the bond we're going to break to make a minus and a plus. We're going to break, I'm going to up to the big screen. This is the bond we're going to break to make a minus and a plus. We're going to produce ions, but you're going to have, say, 90% of it being the basic compound and 10% of it breaking into the ions. 90% of that, 10% of that. So on average, you have mostly not ions and a little bit of ions, as opposed to if I did NaCl, it's going to break into 100% Na and 100% Cl minus. So that's what it means to be a weak electrolyte. It only partially breaks apart. Because technically this is a covalent bond, this OH. But it's a highly polar covalent bond, so it's possible for it to break. You know, I said strong electrolytes are usually ionic compounds and strong acids and bases. We're going to learn about some of these strong acids and bases later. So sodium chloride, that's ionic. KOH, that's a strong base. H2SO4, it's a strong acid. We'll learn about sulfuric acid and potassium hydroxide later. Non-electrolytes are just soluble molecular compounds. This is methanol. SO2 will dissolve. NO2 will dissolve, but they won't really ionize. The weak electrolytes usually have properties of both ionic and molecular compounds. Like weak acids and bases are the most common weak electrolytes. Ammonia, as we'll learn, is a weak base. Acetic acid is a weak acid. That's the acetic acid that I've drawn right there. But, okay. So we're going to split the remaining bit of this chapter into three basic types of reaction. Precipitation reactions and acid-base reactions and oxidation reactions. The first thing is to learn about precipitation reactions. What is a precipitation reaction? A precipitation reaction is a reaction where a precipitate, which is an insoluble solid, forms out of solution. So I'm mixing together two strong electrolytes. Two solutions that contain strong electrolytes. They've completely dissolved, they're completely broken up. And when the byproduct is not just a non-electrolyte, it's actually not soluble, an insoluble solid. That essentially, as I mix them together, something crystallizes out of solution and sinks to the bottom. You basically mix two colorless liquids and suddenly a colored solid forms. Suddenly it's like something becomes visible. Now here's some rules I will give you. Keep in mind, I can also give you a table. If I don't have the table already posted, I will post the table and we'll look at it together. But there's a cross table we can look at that will tell us what's going on. So long as a product is insoluble, a precipitation reaction will occur. These rules will help determine whether a precipitate should form. But the first two rules are the most important. So in order to do a reaction and consider whether a reaction would happen, we have to first consider what are the compounds that should form, and then use the rules to see if a precipitate will form. So in a given reaction, and you're asked what's going to go on, if I say sodium hydroxide plus iron chloride goes to iron hydroxide, I'd have to first go, what should be the product? What should be the product? Most of these precipitation reactions will be a double displacement. What does that mean? The sodium is going to flop with the iron. So sodium is going to take the place of iron. And then, so sodium goes to sodium chloride. And iron would go to iron hydroxide. So they swap places. Once I have those in place, I'll look at these rules. And I'll see, would a solid form? And if a solid forms, this is going to be a precipitation type reaction. So the first rule has to do with cations. Anything from group 1, so group 1 is lithium, sodium, potassium, rubidium, cesium or francium, and also ammonium, NH4. All these guys are always soluble all the time. So no matter what I mix sodium with, sodium is always dissolvable. And rule 2 is nitrate, chlorate, perchlorate, and acetate are always soluble all the time. So anytime you have these guys, they will not form a solid. The only way to get these guys to form a solid is by removing all water. When you remove all water, they have no choice but to stick together. But in the meantime, as long as there's water present, they will dissolve. Before I go any further, I realize, so what is actually happening in precipitation? As I said, when you're dissolved, the ions are being separated like two star-crossed lover in a big crowded dance. They're being held apart. There's giant crowds. Well, in an insoluble solution, the attraction is just too strong. They're going to push their way through the crowds, get to each other, and connect. And they're going to be solid and inseparable after that. Once you form a precipitate, if you have a good attraction, it's going to beat out the water. The waters can't stop them. They're going to be connected, and they're going to form a solid, and they're going to leave. They're going to leave that dance together happily ever after. So, in this precipitation, rule 3, chlorides, bromides, and iodides are soluble most of the time, except when mixed with silver, lead, or mercury. So a silver chloride precipitates, but iron chloride would dissolve. Lead iodide precipitates, but scandium iodide would dissolve. And so we have these rules that essentially say, if I have a chloride and it's mixed with these three metals, any of these three metals, it will form a solid. Rule 4. Excepting for rule 1, carbonates, sulfites, phosphates, and chromates are usually insoluble, meaning they form solids. Sodium carbonate is an example of the exception, except for rule 1, where sodium will always be soluble all the time. So sodium carbonate would be soluble, but beryllium carbonate would not. Lithium sulfite would be insoluble. Zinc sulfite would not. So rule 4 says these are guys don't like to dissolve except for rule 1. And then rule 5, except for rule 1 and barium. So barium is another exception. Hydroxides and sulfides are typically insoluble. So that means barium hydroxide dissolves, calcium hydroxide does not. Except for rule 2, silver, mercury, and lead are usually insoluble. So silver doesn't really matter what it's mixed with. It's usually insoluble. And then finally, with the exception of calcium, strontium, and barium, and the ions listed on group 6, all sulfates are soluble. So sulfates are usually soluble, except for silver, mercury, and lead, calcium, strontium, and barium. Let's see. Okay. I just want to look ahead. Okay. So one thing part of this chapter is going to be writing out the reaction that's going on. If I give you a description of what's going on, you should be able to write out a chemical equation. You should be able to classify this as a precipitation reaction. You should be able to state what's the driving force, essentially. So aqueous compounds, when they're dissolved in water, can be classified as electrolytes and non-electrolytes. Okay, ionic compounds can be separated into the cations and anions. This is only true for ionic aqueous compounds. Solids, liquids, and gases will not separate. One of the things I'm trying to bring about here is so when we represent an aqueous solution, lead nitrate, aqueous, is really saying this: lead 2+ aqueous and 2 nitrate atoms aqueous. Note the nitrate is left as one unit. We don't split this into N's and O's. Nitrate is one anionic unit and it stays together. That subscript becomes the coefficient because essentially, as a solid, you have lead with 2 nitrates sticking to it. When you dissolve it, you're essentially breaking that sticking point and 2 nitrates float off. So saying lead nitrate aqueous is saying that we have a solution with these 3 things floating in it. 1 lead and 2 different nitrates floating surrounded by water. And what we're going to look at here is first writing a chemical equation. 2, writing an ionic equation where we split apart all aqueous units into their total ions. And then eventually we're going to get to the net ionic equation. Okay. Yeah. I want to actually, before we get there, do a little practice of this. This is in the slide, but this is for the benefit of all, ideally. So if I were to say hydrochloric acid plus silver nitrate solution gives silver chloride solid and nitric acid solution. So breaking that down, hydrochloric acid solution, HCl plus silver nitrate solution goes to silver chloride solid and nitric acid solution. So right here, I've written the overall chemical equation. I've essentially stated that what is our two reactants, what is our two products. I've included all phases. Now, it just so happens they're all balanced. I don't have to do any balancing. Thankfully for that. Now, if I were to turn this into the net, or not the net, but the ionic version, I would take, for the ionic, I would take every part that is aqueous and I would separate it in the cation ionic anion pair. Any solids we would leave together. Any solids I would leave together. So, in this case, I would have H plus aqueous, Cl minus aqueous, plus Ag plus aqueous, and NO3 minus aqueous, all on the reactant side, yields AgCl solid and H plus aqueous and NO3 minus aqueous. So I've split apart all the aqueous things into cation-anion pairs. We have generated the total ionic equation. You would leave all solids, all liquids, all gases together. Hopefully you'll see something here, because it's going to lead to our next step when we do the net ionic equation. You'll see there is an H plus in the reactant side, an H plus in the product side, a nitrate in the reactant side, a nitrate in the product side. We're eventually going to cross those out and get the net ionic equation. The net ionic equation being the equation that shows just the driving force. If I cross those out, what could we say is happening? Silver plus chloride snap together to form an insoluble solid. That is the driving force that forces this reaction to go. I'm going to do one more example of this before we go to net ionic. So another example, I'm just thinking up in my mind, sodium carbonate, aqueous, sodium carbonate solution, plus hydrochloric acid solution, yields sodium chloride, salt, solution, water, and CO2, gas. I would have to balance that. And let's see. And I'd have to balance that. Now, with that in mind, once again, we split apart all the pure solids, all the aqueous along the lines, while leaving the liquids and the gases alone. So you would have 2 Na plus aqueous, 1 CO3, 2 minus aqueous, 2 H plus aqueous, and 2 Cl minus aqueous. And this yields us 2 Na plus aqueous, 2 Cl minus aqueous, H2O liquid, and CO2 gas. I can't break apart the gas. I can't break apart the liquid because they are not ions. They are molecules. Either this is bubbling out or this is the solvent. Now we've made a pure molecule liquid. So what can we do? We're going to eventually be able to cross out these that are duplicated and these that are duplicated. So what are we seeing? What is the net reaction? What is the driving force? We're seeing that when we mix H plus, which is the basic acid component, into carbonate, carbonate will produce a bubbling gas and water. That was one of the questions that got asked on the pre-lab of the Everyday Chemicals lab, dealing with how can you detect carbonate? Well, in the presence of acid, it would produce a bubbling gas. And so these are just examples of we're writing an equation and we're turning this into the total ionic equation. And I'm just trying to preview real quick where we're going here. And that's that we want to be able to write the net ionic equation. So when we take lead nitrate and potassium chromate, we can split this into lead chromate and potassium nitrate. If we then take that to ionic, we split all the ions up, leave the solid by itself. The idea here between the total ionic and the net ionic is we have what's called spectator ions. These ions that stay identical from reactant to product. They don't change charge, they don't change amounts, they don't do anything between reactant and product. They just float there watching. They are the spectators. Now, we can cross these guys off because they don't actually contribute anything to the driving force. So when we cross off all the spectators, we get the net ionic equation. The ions that only directly participate in this reaction. Please note, some reactions may have 0 spectator ions. All ions may participate. In that case, the total ionic equation will be same as the net ionic equation. But if you get a situation where all ions are spectators, then we can say that no reaction has actually occurred. In the bottom case, potassium nitrate, calcium chloride goes to potassium chloride and calcium nitrate. If they're all aqueous, they all cancel out. No reaction is actually said to happen. This would be a simple case of we do a double displacement. You can write, they say they swapped partners. But if at the end of the day, there's no connection between any of the ions, there's no attraction, and they can swap back, there's no real reaction. There's no chemistry going on. They leave, they go home, back to their sad ionic lives, empty, without a partner. So we need a driving force. We need a solid. We need a liquid. We need a gas being formed that's going to make them leave the party, go home, have a life. So we will need something to occur. Okay, let's see. Please. Okay. There are some acid-base neutralizations. So the precipitation is but one type of reaction we'll have to deal with. Acid-base neutralizations are very similar. An acid will neutralize a base, and the neutralization will form an ionic compound in water. Almost all acid-base equations, by definition, will form water as a byproduct. Most of these guys, when we write the net ionic equation, will just be H plus OH minus and water. Most of these guys, an acid-base neutralization. And that's going to be the situation when dealing with a strong acid or strong base. This reaction that we just did is an example of one of the exceptions. It's not H plus OH gives you water, but you'll notice that water is formed as a byproduct. Carbonate is a weak base. Carbonate is we produced water as a byproduct. Acids and bases will want to form water, and that pure liquid will stay around. The only problem is weak acids are weak electrolytes, so they will not ionize when we write the ionic equation. So the example I give, HCN plus NaOH goes to water and sodium cyanide. So the net ionic equation would be HCN plus OH minus goes to water and cyanide minus. Because this guy, HCN, is a weak electrolyte, it screws everything else up. It's not allowed to just fully separate. Oh, God. And the last bit, I want to see. Oh, God. Okay. I'm trying to see how much further I got. 15. Yeah. We're going to, I don't know how much more slides we got, but once we finish these slides, I will be looking at some example problems. If we don't have enough time to do the example problems today, I will produce a secondary video for Wednesday of just working through problems of what this might be like. So, because this is kind of jumping around this. But the last type of reaction will be oxidation reduction reactions. So, or often referred to as redox. Redox. A redox reaction is when the charge of a given ion changes in the course of the reaction. For example, if iron 3 were to go to iron 2 plus, what can we say has occurred? It has gained an electron. Because 3 plus, 2 plus means it's 2 electrons short of neutral. So in that period, it has gained 1 electron to go to change oxidation states. The charge of each element by itself or within a compound is known as the oxidation number or the oxidation state. We can use these rules to assist us to figure out what is the oxidation state and whether it's charged. So all pure elements, anytime you see a pure element, whether it be a diatomic gas or just an individual element sitting there doing nothing, the charge can be considered to be 0. Any monoatomic ions would have an oxidation state equal to the charge. So if I just add iron 2+ floating around, what's the charge of iron? 2+. So don't overthink that. Don't overthink that. It's the most obvious, but it still needs to be stated. Now here's where it gets a little trickier. The sum of the oxidation states in a formula is equal to the charge of that formula. So if I had iron chloride and it's neutral, the sum of iron and the sum of chloride must be equal to 0. So we have to figure out what is the charge of iron and the charge of chloride, knowing that those summed up equals 0. So we got a couple other rules. Hydrogen, which remember is in group 1, is typically +1, unless it's bound to a metal. Oxygen in the compound is typically -2, with the exception of peroxides. I think I'm going to throw any of those at you. Group 1 metals in a compound will all be +1. Group 2 metals will always be +2. We kind of did these already. Some of this stuff is the same stuff we've gone over. Halogens are usually -1, especially fluorine. Everything else is context clues. Everything else is context clues. So now we can really focus on the metals, the transition metals. So in the case, potassium phosphide, I'm saying, what is the charge of potassium? What is the charge of the phosphorus? Well, potassium is group 1, so it's going to be +1. There's 3 potassiums, so the phosphorus must be -3. Magnesium hydroxide. Well, there's magnesium is group 2, so it's going to be 2+. Hydroxide is each -1, but each hydroxide is made up of -2 oxygen and +1 hydrogen. The hard one right here is iron oxide. So oxygen is 2-. 3 oxygens makes it -6. 2 irons means the sum of both irons would be +6. So if I take 6 divided by 2, what do I get? +3. So the oxidation state of iron would be said to be +3. The oxidation state of oxygen would be -2. This is another slightly tricky one. Nitrate. Nitrate 1-. Oxygen is said to be -2. So 3 oxygens makes this -6. Nitrogen plus the -6 would be said to sum up to be -1. So X -6 equals -1. Well, 5 - 6 is said to be -1. So in this case, nitrogen would be +5. CO2, 2 oxygens, each at -2 is -4. So -4 minus blank, well, 4 minus 4 is 0. Carbon is said to be positive 4. Same one, SO4 2 minus. 4 oxygens be negative 8. Negative 8 plus 6 would be negative 2. Now these last ones, I'm not even going to, I'll do the first two. The last one is just a F you right now. So it's like now. Potassium is plus 1. Oxygen is negative 2, so a total of negative 8. 1 minus 8 is negative 7. So rhenium would have to be positive 7. Magnesium is plus 2. Oxygen is 7 times 2, negative 14. So we have a total of negative 12 times 2x. 12 divided by 2 is positive 6. And this iron hydroxide, if you tried to do this, you'd come up with something really stupid. O is 4 times 2 is negative 8. How is negative 8 evenly divisible by 3? You'll see, no, that's not evenly divisible. You're not going to get a charge of 2 and 2/3. What happens is iron is actually a mixture of 3 plus, 3 plus, and 2 plus. That's a weird iron structure. So, but yeah, I just want to see how many. Okay, yeah, we got like 3 more slides left. I am not gonna do them today. I will put together a small video for Wednesday. If you want to show up and ask some questions, go ahead and come ask some questions. But just watch the video later. Don't worry about zooming in because I'm not going to do a whole class video. In fact, I might put this video out later today so you can get that done. So you don't have to worry about paying attention over fall break. But basically, right now, as we go forward, this is the last chapter for the test material. Come Monday after fall break, we'll start reviewing for said test and be working on that and be ready for that within a week or so after fall break. Now, I'm not sure exactly when all the homework's due. I'll have to check that, but that is the plan. We're going to finish this material, be ready to start reviewing for the test come Monday. But I want to go over this little thing and then do practice problems. Just pull some stuff from this chapter. What does this actually look like in practice on Achieve? So we can see not just this metaphorical, hypothetical situation, but real life, what might a test question actually look like? Because right now it's kind of like we're just barely skimming a topic without any math. And so I'd like to actually show you what we might actually expect.